All right, welcome to this explainer. Today, we're embarking on what's basically a massive scientific detective story. We're looking up, way up, to decode the secrets of the sky, right from space. I mean, have you ever wondered how supercomputers actually know what's a cloud and what's, say, just a really cold mountain peak? Well, we're going to explore the incredibly clever physics and math used to automatically detect clouds from satellite data. Specifically, we'll be breaking down the renowned Apollo scheme. Here's our roadmap for today. First up, a quick intro to remote sensing. Then we'll look at the hurdle of clouds. After that, the core of our mystery, the 5 algorithmic tests. And finally, the applications of detected clouds. Let's dive in. Section 1. Introduction to Remote Sensing, the Eye in the Sky. You know, we've been looking down at our planet from above ever since the launch of the very first Earth-observing satellite back in 1960. But today, our ultimate investigative tool is the Advanced Very High Resolution Radiometer, or AVHRR. And it doesn't just take pictures. It actually scans the Earth across multiple, highly specific wavelengths of electromagnetic radiation, from visible light all the way to thermal infrared. It essentially lets us see what the human eye literally cannot, giving us this continuous, high-resolution feed of the Earth's surface and atmosphere. But here's where we hit a pretty massive roadblock. Section 2, the hurdle of clouds, nature's contaminant. So, clouds are a huge headache for atmospheric scientists. Why? Well, they actively alter the Earth's energy budget through scattering and absorption. They totally interfere with our attempts to measure the atmosphere's temperature and moisture. And worst of all, if a supercomputer accidentally mistakes a cold cloud for the ocean, boom, it corrupts our sea surface temperature data. If it mistakes a cloud for land, it completely masks our land surface temperature and vegetation indices. So we absolutely cannot retrieve this crucial climate data without first isolating and removing that cloud interference. What this means is that before any real analysis can even begin, we have to play this massive game of sorting. Every single data point, or pixel, from the satellite has to be sorted into one of 3 very distinct buckets. It's either cloud-free, cloud-filled, or partially cloudy. Only after that sorting happens can we actually trust our climate data. And that brings us to Section 3, the 5 algorithmic tests, the APLL scheme. So how exactly do we sort those millions of pixels? Well, enter our hero, the Apollo scheme, developed by Saunders and Kriebel back in 1988. It's this highly sophisticated toolkit that uses 5 specific algorithmic tests to interrogate every single pixel. We've got the gross IR threshold test, the spatial coherence test, the dynamic visible reflectance test, the Q ratio test, and finally the brightness temperature difference tests. Let's break them down. Okay, test 1 is the gross IR threshold test. This relies on the 11.0 micrometer thermal channel. Think of it as basically taking the Earth's temperature. See, clouds generally take on the temperature of their surrounding environment, right? And since the atmosphere gets colder the higher up you go, cloud tops are usually freezing. So this test looks for those obvious cold tops of high clouds and flags them the second they stand out against the relatively warmer land or ocean surfaces down below. Moving on to test 2, which relies on spatial coherence, or local uniformity. Imagine analyzing a 3x3 array of pixels. It's kind of like feeling a surface in the dark. A completely cloud-free ocean is going to have very low temperature variance. It feels like smooth glass. But if that pixel array is sitting right on the edge of a cloud, or it's partially cloudy, the temperature wildly fluctuates from a cold cloud to a warm ocean. It feels like a bumpy sponge. That high variance instantly flags the presence of a cloud edge. Next, test 3 brings us into the daylight with the dynamic visible reflectance test. When we plot how different surfaces reflect sunlight across various wavelengths, a really distinct pattern emerges. Clouds have remarkably high solar reflectivity at visible wavelengths, compared to stuff like bare soil or a forest canopy. So if a pixel is blindingly bright in the visible channel, it's highly likely to be a cloud. But wait, snow follows a really similar pattern. Snow is also incredibly bright in visible light. And that is exactly why visible light just isn't enough. In a standard natural color composite, the bright white snow in the mountains looks totally identical to the bright white clouds off the coast. But by aggressively pulling apart multi-channel data, specifically using near-infrared channels, we can create a false color composite. Because snow absorbs near-infrared light while clouds reflect it, the snow suddenly shows up as red while the clouds stay white. Boom! Those visual similarities are instantly shattered. Building on that reflectance data, test 4 is the Q ratio test. This evaluates the ratio of the near-infrared channel to the visible channel. Think of this one like a balancing scale. Over a cloud, both of those channels are highly reflective, so the ratio balances out perfectly to a value right near 1.0. But over land or water, the reflectances are vastly different between those two channels, and the scale tips dramatically. If the math hits 1.0, you've definitely found a cloud. Finally, test 5, the brightness temperature difference tests. To reveal hidden cloud structures, this test uses a split window technique. Basically, it subtracts the values of two thermal channels, like the 11.0 micrometer minus the 3.7 micrometer channel. It works exactly like putting on a pair of polarized colored sunglasses. Because water clouds and ice clouds emit thermal energy slightly differently at these two specific wavelengths, subtracting them makes these invisible textures just pop. Suddenly, incredibly tricky obstacles like thin cirrus clouds or nighttime fog are violently contrasted against the ground. All right, Section 4. Applications of detected clouds, the twist. So we've spent this whole time treating clouds as nature's contaminant, right? Like the villain of our story. But what if clouds aren't just an obstacle to clear away? What if they actually hold invaluable meteorological intelligence? Turns out, once we confidently assign a pixel into that cloud-filled bucket, it becomes an absolute goldmine of data. We can extract incredible thermodynamic and microphysical parameters. We can calculate exact cloud top temperatures, determine their optical depth, figure out their phase, like whether they're made of ice crystals or liquid water droplets, and even analyze their total liquid water content. We're literally using the obstacle itself to study the atmosphere. And it's not just the fully cloudy pixels that are valuable. Even those messy, partially cloudy pixels serve a really vital purpose. They're used to calculate fractional cloud cover. This is a highly critical mathematical metric that gets continuously assimilated into the massive supercomputers running our global climate research and our daily mesoscale weather forecasting models. Literally every single pixel plays a part. You know, the quest for an accurate cloud mask has been driving atmospheric science since 1960. Next time you look up at the sky, consider the immense, invisible mathematical puzzle happening right above your head. Every single cloud is being scanned, tested across multiple wavelengths, and categorized in real time by algorithms like the Apollo scheme, continuously feeding the models that help us understand our changing planet. So, with all that data constantly flowing down from space, what other secrets do you think the sky is hiding? Thanks for joining me on this explainer, and keep looking up.